Right. We're skipping the fluff and jumping straight into everything you need to know to absolutely smash the AQA GCSE Computer Science Paper 2. This is a rapid-fire, fact-dense cram session, so keep your eyes locked on the screen. Let's go.
Section 1. Data representation, compression, and size.
So, look, literally everything inside a computer is just binary, switches that are either on or off. And this builds into a really strict data hierarchy. It starts at the absolute smallest unit, a single bit, just a 0 or a 1. Grab 8 of those and you've got a byte. After that, it scales up perfectly. A kilobyte, megabyte, gigabyte, and terabyte are each exactly 1,000 times bigger than the one before it. Oh, and a quick side note on hexadecimal. It's literally just a shortcut we use to make binary easier for human eyes. One single hex digit perfectly matches 4 binary digits.
When you're doing binary math, honestly just approach it exactly like normal math, laid out in columns. 1 plus 1 is 0, carry the 1 to the left. 3 ones in a column, that's 1, carry the 1. Simple, right? Now for binary shifts. A left shift basically multiplies the number by 2. A right shift divides it by 2. But here is the absolutely crucial thing to remember. A right shift always rounds down. Why? Because that rightmost digit literally just falls off the end and gets permanently lost.
Okay, to shrink all this data down, you basically have to make a choice. Lossy versus lossless compression. Lossy is, well, it's brutal. It permanently deletes parts of your file. Now, that's fine for images or sound where a tiny drop in quality doesn't really matter. But for text documents or executable programs, no way. You cannot afford to lose a single byte. That's where lossless compression saves the day. Methods like Huffman coding or run-length encoding don't delete anything. They just rearrange the data way more efficiently, so you can perfectly recreate the original file.
Moving on to Section 2, Computer Systems, Hardware, and Logic.
All right, there are 4 Boolean operators that make up the logic gates inside a processor. Not is easy, it just flips the input. AND means both inputs absolutely must be true. OR means either one can be true, but you really need to pay attention to XOR. That stands for exclusive OR. It operates exactly like how we use the word OR in normal everyday conversation. You know, you can have a pizza or a burger, but you can't have both. Only one input can be true, never both.
Now, what's really interesting here is the massive trade-off you face when translating your human-readable code into machine code. A compiler grabs the whole file and translates it in one massive go. It produces a super-fast executable file and hides your source code. But the catch? You don't find out about any bugs until the very end. An interpreter, though, runs line by line. It's definitely slower, and it exposes your code for anyone to see. But the massive upside is that it throws an error immediately when it hits a bug. This makes it absolutely excellent for fast debugger. Okay, let's look inside the von Neumann CPU architecture. We've got 4 distinct parts. The arithmetic logic unit, or ALU, does the actual math. The control unit oversees the whole operation, kind of like a manager. The cache is this ultra-fast tiny bit of memory located right next to the processor, and the clock synchronizes the entire system using steady electrical pulses. Keep this in mind. The clock speed, the number of internal cores, and the size of that cache are exactly what dictate the CPU's overall performance.
So the CPU is constantly running the fetch-execute cycle. Step 1, fetch the instruction from memory. Step 2, decode it to figure out what it actually means. Step 3, execute the instruction. And listen up, because here is a specific, kind of confusing detail that exams absolutely love to test. If an instruction needs extra data to actually work, that data is fetched after the instruction, specifically during the execute stage. When it comes to main memory, you've got to remember the power-off test. RAM is volatile. If the power cuts, boom, it is totally wiped. It only holds the programs and data you currently have open. ROM, on the other hand, is non-volatile. It safely keeps its data even with 0 power. And that's exactly why it holds the crucial boot-up program that tells your computer what to do the second you turn it on.
Now, all this builds into long-term secondary storage, which basically falls into 3 main buckets. You've got magnetic hard drives. These give you massive capacity for super cheap, but they rely on fragile spinning disks. Then there's optical disks, like DVDs, which are really portable but scratch easily. Finally, solid-state drives, or SSDs. These are highly durable and incredibly fast. Actually, they are steadily replacing hard disk drives purely because they completely lack any fragile moving parts. They're just better.
Next up, Section 3, Networks and Protocols, Global Connectivity.
When you're arranging a network, a star topology connects everything to one central hub. It's incredibly scalable and super easy to plug new devices into. But if that center node fails, the whole network dies instantly. Contrast that with a bus topology, which just uses a single central wire. It's way cheaper to build for sure, but you take a massive performance hit. Why? Because data signals traveling down that single wire constantly crash into each other, creating nasty data collisions.
All right, you've absolutely got to memorize these 4 protocol layers. They're what ensure devices around the globe can speak a common language. The application layer handles things like web and email. The link layer is your actual physical connection, think Wi-Fi or Ethernet. But pay really close attention to the transport layer. TCP crucially checks for and handles data errors by resending lost packets. UDP, however, completely ignores errors to prioritize raw speed, and that's exactly why UDP is the go-to for live gaming and streaming.
Section 4. Cybersecurity. Let's look at threats and defenses. In cybersecurity, threats fall into 2 distinct buckets. First, we have human threats. This is social engineering, basically tricking you into giving up info. That could be blagging with a fake story, phishing via sketchy emails, or literally shouldering, just looking over your shoulder to steal a password. Second, we have software threats, meaning malware. Viruses replicate themselves inside your real programs. Trojans trick you by hiding inside useful software. And spyware? That just quietly records your keystrokes in the background.
To find vulnerabilities before the bad guys do, companies will actually safely hack themselves using penetration testing. A white box pen test simulates a rogue employee. The tester is essentially given full internal knowledge of the system. A black box pen test, though, simulates a random external attacker. The tester starts completely blind with zero prior knowledge of the company's networks.
So what are our defenses against all this? Well, firewalls filter incoming data packets based on strict rules. MAC filtering blocks specific pieces of hardware from connecting. CAPTCHAs stop those annoying automated bots. Biometrics use your unique physical traits, like a fingerprint, to prove you are who you say you are. But the ultimate tool? That's encryption. It completely scrambles your data so that only a person holding the exact mathematical key can read the text.
Moving fast, Section 5. Relational databases, SQL, and tables.
Relational databases use linked tables to stop redundant data, but to link those tables, you need keys. This is a highly testable difference, so listen up. A primary key is a field that completely and uniquely identifies a record in a table. Think of it like a unique student ID number. A foreign key is simply a primary key from a different table that has been brought over to create a relationship between the 2 tables. They have to match up perfectly for the link to work.
To actually search through those databases, we use SQL. Lock this formula right into your memory. You select the fields you want to see from the tables they live in, where a certain condition is met, and you order by a specific field. Seriously, memorize this exact structure, right alongside your standard insert, update, and delete commands.
Finally, Section 6. Impacts of computing, ethical and legal.
Now, this section isn't just about rote memorization. When evaluating an exam scenario, anchor your answers in these 4 categories. Ethical impacts deal with right and wrong, like automation destroying human jobs. Environmental impacts cover physical harm to the planet, like the massive mountains of toxic e-waste generated because we buy a new smartphone every single year. Legal impacts cover strict laws around data protection and IP theft, and privacy impacts relate to things like smartwatches constantly vacuuming up our personal data. And this brings us to the ultimate thought experiment for your exam. If a fully autonomous, self-driving vehicle makes a decision that results in a crash, who is legally and ethically responsible? Is it the driver who wasn't actually driving, the corporate manufacturer, or the individual programmer who wrote the algorithm? Think about it, because that's exactly the kind of question they're going to hit you with.